So we've already come to understand, and it's been expressed many times, that we want to avoid absorbing aerosols in our geoengineering. And so, of course, given the group that is working on this, we're going to look exactly at absorbing aerosols because we think bad ideas are good ideas. So where's the clicker? No, seriously. So the idea here is to take a different approach to geoengineering, solar radiation management, and instead of trying to modify the short wave in, we're going to try and enhance the long wave out by heating the stratosphere. And in theory, this should work, but the question is, what are the side effects? And so we can go to a risk world on that. So we have a paper in review, almost accepted, led by Hao He. And I'm going to presented these results in November, and I'll just go briefly in them. But there's a big altitude dependence on the effect of absorbing aerosols on radiation. High up in the stratosphere, say 10 millibars or so, you get actually net cooling from absorbing aerosols because of the increased long wave emission as you heat the upper stratosphere. And it turns out that per unit mass, the long wave absorbers are much more efficient, about a factor of 12 more efficient than sulfate at cooling the atmosphere or cooling the planet. So you can get with 0.5 teragrams, you can get the equivalent of black carbon, you get the equivalent cooling of the planet of, 7 teragrams of sulfate. So if everything scaled with mass, this would be better, but not everything scales with mass. Are you sure, Tom, it doesn't scale with mass? Anyway, so just to illustrate this, these are just two experiments with coupled models. The top lines are showing surface temperature response to increased aerosols. The blue line is a response to 0.5 teragrams of black carbon at 10 millibars, and the red line is the response to 5 teragrams of sulfate at the same altitude. But it doesn't really matter. Sulfate doesn't have a strong dependence. It's just how high you hold the sunshade over your head doesn't matter that much. And they both affect precipitation globally, and the regional patterns are very similar. And it's, once you start cooling the planet, first and second order responses to cooling are largely sort of similar. They have a very, what you can see here, this is on the top, on the left, it's sort of a way to estimate climate sensitivity. And 5 teragrams of sulfate has a lower intercept, both in X and Y, meaning it's smaller radiative forcing and also smaller equilibrium climate sensitivity per unit mass than black carbon. But the hydrologic sensitivity is all in a line. So the difference in hydrologic response between these is connected to the difference in warming, right, or cooling. And this gets us to what we're doing now, is that what these different aerosols are doing isn't just cooling the planet. By design, the absorbing aerosols cool the planet by heating the stratosphere. The objective is to heat the stratosphere, and in doing so, increase long wave emission, break the greenhouse effect a little, and that leads to cooling, which it does. But it leads to other things. Among them is you have a drying of the lower stratosphere, and you have a reduction in cloud fractions in the lower stratosphere. Some of that can be understood just by thinking about increasing stability there, less transport of moisture, other things into the stratosphere. And we're trying to better understand these, and we're also trying to move to more comprehensive models, more complex models. These were done with prescribed aerosol concentrations, as we've seen today, and we should know before. You don't get to put in concentrations. You put in emissions, and you get concentrations through complex processes, right? So what are some ongoing steps? The ones I'll touch on today are the red ones. What impacts on stratospheric circulation and chemistry, and can we move to more emissions-driven rather than concentration-driven experiments? But we're always going to keep these, at least for now, in a very idealized context, because there's a lot to learn from idealized experiments without going to very comprehensive forcing. And then what about regional climate changes and particular extremes? And I'll start with that. This is some work led by Aidan Mahoney, who's a graduate student at the University of Miami. What he found was, and this is motivated by trying to understand what the potential impacts on tropical cyclones of the stratospheric temperature changes would be, is that in targeted perturbation experiments, they're in the stars. This is with a tropical cyclone permitting model, GFDL's HIRAM. You get a very strong, if you start perturbing temperatures in the stratosphere, you get responses in potential intensity. It's a theoretical upper bound on hurricane intensity. And those scale very well with the dependence of potential intensity on stratospheric temperatures across the high-res MIP experiments and the CMIP experiments. And what's kind of interesting about this is that a lot of the spread in potential intensity in CMIP models comes from their representation of stratospheric temperatures. There's a huge range, more than we expected to see in lower stratospheric temperatures in these CMIP models. It's about 16-degree variation in their climatology. And that is sort of can be associated. You can work through the theory to show that's responsible for most of the spread in potential intensity. So getting our stratospheres better would help us better understand tropical cyclones. So if the tang of some of this work to better understand stratosphere is better understanding tropical cyclones, I think that's good. Now, Hauge has done some experiments we've been running a 50-kilometer TC permitting model, tropical cyclone permitting model, with fixed sea surface temperatures, and we can ask what the response of global tropical cyclone frequency, directly simulated, is to aerosol injection of either absorbing, we call it black carbon, but just think of it as an absorbing aerosol on the left, or scattering aerosol on the right. It's got sulfate properties, but I think scattering is scattering at this level of complexity. And what you can see is that in a fixed ocean temperature world, black carbon injection tends to have a suppressive effect on TCs. That has to do with warming the stratosphere, decreases potential intensity. Potential intensity, you can think of it as a Carnot heat engine analog, and the outflow temperature of the storm is up there. And so if you heat the bath temperature of the engine, it runs less efficiently. So heating the stratosphere makes the storms less efficient. However, when you start then allowing the ocean to respond to the aerosols, you get much less. These are anomalies in tropical cyclone response. The number one thing that you should see there's a lot of variability. The climate system is really chaotic, and so this is 150 years of simulations. And so you could imagine the detectability of the aerosol signal on TCs is going to be very low. And if you might imagine, people start throwing aerosols in the sky and claiming one thing or another is caused by it, which it could all be just noise. And so this is really, the detectability question is going to be crucial for any governance and feasibility of this. And I don't know how you communicate it, because scientists have a hard time with it. We point at all sorts of things that we should know better and ascribe a cause to them when it's probably random. Anyway, so the response of ozone, when you start heating the atmosphere the stratosphere by 30 degrees, you might start wondering what ozone does. And so we've been taking a two-step approach to this. And we're going to add a third soon. But one is we're using a linearized ozone model, simple, but we can understand it. And so we can see what it does and what drives things. And then we're using interactive chemistry model out of GFDL. GFDL is 4.1, AM 4.1, to sort of see the more comprehensive model if they give similar results in the simple model. And so Jimbo Shi, who's joined us recently from Department of Energy, but is now at Princeton, has implemented this simple linearized ozone estimator called LinOz. You have these rates that depend on both sort of the state of ozone and the climate or the weather, and you can estimate sort of the ozone response to different meteorological perturbations. You can do it offline in the model. And that allows us to do it with our physics-only models, right? And then we can get a rough ultraviolet index changes following sort of this idealized called column ozone changes and see what happens. This is Jimbo's initial results. So each, say the upper left is what happens from black carbon injection at, I think it's 3 millibars or 6 millibars. And you see that there's on the left set of panel, then you go down lower in the stratosphere where the black carbon injection is. And what you see is that there's heating where you inject the black carbon. The higher you inject the black carbon, the higher the heating. And then the ozone percent changes. What you can see is that they're blue where you have the heating. And that makes sense, right? So you're increasing these rates and you expect the ozone to go down. But what was surprising to me, but maybe not to other people that know more about ozone, was that below the decreases in ozone, you had increases in ozone. We think those may be sort of circulation and supply result. I don't know what, and yeah, Timofey, you know what they're for?
Yeah. Okay. Now, I think it's the self-shielding. You simply destroy ozone above, you get more ozone.
Yeah, it's a UV. Yeah.
Just goes down because it's also linearized ozone chemistry, so it must be not dynamics because.
Yeah, that's right. It's not the dynamics.
Yeah, so I think it's UV shielding or self-shielding. Yeah.
Not in this one. Yeah, you're right. But anyway, the other bit is that what Jimbo did is on the left, what you have is column ozone integrated. So you start at the top of the atmosphere and you integrate down to any level. So the value you see at a level is the column ozone above you. And so you see a decrease in column ozone over the places that have heating and that decrease in ozone, but because you have the increase in ozone below them in these estimates, you actually, especially in the tropics, so once you get near the surface, or this is still at the bottom of the stratosphere, you don't really have a decrease in column ozone. There's a little bit of offsetting. And so when you put this UVI model through it, in the polar regions, there is an increase in UVI, but in the tropical regions, there isn't in the troposphere. This is a very simple calculation, but it's just sort of a first thought, and what it shows is that there is some complexity here. It's not just heating gives you less ozone, right? And so what that means is that we need to run these more complicated models. And here, Haoje with Wencheng, first off, since November, we've transitioned to a new computer. So we had to report all our codes, import new codes, get them to run. We got them to run. We have everything running. These are hot off the press results. By the way, I want to just advertise, our new computer is water cooled. So it runs on 50% the energy that it otherwise would have. And so although I'd love it to run on 0% of the energy, it's great that we're contributing less to global warming in these experiments. So we have, what Haoje did is now this is now a version of the model with no chemistry, but it's prescribed, it's calculated ozone, sort of aerosols from emissions. And so we want to see what happens to aerosols when we emit them, because they have, this idea of self-lofting and other properties. And so injecting on the top black carbon at different levels for 1 year, you inject it for 1 year, so that over that year you inject a teragram. And then the bottom, you inject over 1 year 15 teragrams of sulfate aerosol at different levels. You see that when you inject the black carbon and the sulfate higher in the stratosphere, they stay there longer, and the black carbon stays there more longer, right? So there's evidence for this self-lofting, and so 3 years, 10 years out, you have about half the black carbon still in the upper stratosphere. From the point of view of efficiency of keeping a concentration up there, that is a good thing. From the point of view of we don't know what this is doing, and we'd love to pull the brake at some point if we had to, this is not good news. So we really want to be sure. The ERF, the effective radiative forcing, you see that you get from 1 teragram of black carbon emission globally, you get about a 4.4 watt per meter squared reduction of effective radiative forcing. And so you have to inject a lot more sulfate to get the same ERF. Wenchang has then implemented the interactive chemistry version of the AM4 model. This is AM 4.1. I don't believe, and I wish Larry and Vaishali were here, who are our colleagues at NOAA's GFDL on this project, but they, as you may know, NOAA is having a hard time traveling if you're an employee of NOAA, and so they're not here. So I'm not going to be able to give you complete answers about the chemistry in AM 4.1. It is, I believe, less comprehensive than the NCAR model's chemistry, but it is more comprehensive than no chemistry at all. And so what Wenchang has done is 2 experiments, one injecting 1 teragram of black carbon over a year at 6 millibars, the other one at 60 millibars, and then similarly 5 teragrams of sulfur dioxide, which then becomes sulfate, at 6 millibars and 60 millibars over a year, and then running the model for 15 years after that and seeing what happens. What we can see is, I should have brought my glasses, sorry. I cannot see. I blame the screens at COVID and not my age. So what we see is, in a globally integrated sense, both the black carbon and the sulfur concentrations move down in the column as they move along. That's using a global pressure level coordinate, although a lot of that is actually meridional movement. And so that as the stratosphere dips down at higher latitudes, you're at a lower pressure for the same altitude, or and what you see is that the lifetime of the black carbon when it's emitted lower is much less, and the lifetime of the black carbon when it's emitted higher is much more, both than the black carbon emitted less at a lower altitude, and then the sulfate emitted, or the sulfur emitted at the same altitude, right? So if you put black carbon high up in the stratosphere, it heats this upper stratosphere, it leads to more long wave emission, and it also stays up there for quite a while. So you can see over here, this is the column load. When you emit it, you have this pulse of emission of black carbon at low levels and also of sulfur at low levels, and then it decays off pretty quickly at 60 millibars when it's emitted at 60 millibars. But the black carbon remains at about half its level. I mean, I'm looking over here. One gets you to about 5 or 6 years out from emission. So you only lose half of the column loading after 5 years, and you get to half much more quickly with sulfate, even emitting high up. And you get this is the clear sky top of atmosphere net radiation response, and you see, as we've discussed before, that the black carbon effect on top of atmosphere radiation is only when it's emitted up high, not when it's emitted low, and it's because of the so you want to heat the upper stratosphere, not the lower stratosphere, if you want to affect the greenhouse effect. And meanwhile, the effect on shortwave from sulfate, it doesn't matter where you emit it, right? How high up it is. The only thing is that when you emit it higher up, it has a longer lifetime, and when you emit it lower down, it has less of a lifetime. So if you're concerned about having to send things up, maybe you put more of it up there. Now this is a plot here where we start getting into the ozone response, and this is ozone mixing ratio on the top right, with purple colors indicating a reduction in ozone mixing ratio. And the right on the top left is black carbon concentrations, and this is in the second year, so after 1 year of emissions. Remember, we've emitted this uniformly, so it hasn't been this concentrated 15 south to 15 north, but it's a uniform emission. And what you can see is that the black carbon goes to the poles, as you would expect from stratospheric circulation. You have ozone reduction in the places and below where you have this strong heating in the stratosphere, which is what you see in the bottom right. But then you also do see some evidence for increases of ozone below the area of decrease of ozone. And so you have decreases of ozone above the maximum in ozone concentration, which is what's shown in the contours in the top right, and increases in ozone below the maximum. So there is some compensation, even though you have, I expected to see huge, like tens of percents decreases in ozone, and we're not getting tens of percent. And then as you progress through the seasons, you see that the black carbon moves north and south, and that you still keep this ozone loss. It does move meridionally with the seasons, and the temperature maxima, or the increases in temperature maxima, which is what we're aiming for, also change with the seasons. Yeah, I'm going to be done with this soon. And then when you go in northern hemisphere summer, northern hemisphere summer, yes, southern hemisphere winter, you see a lot of black carbon low in the stratosphere over the Southern Ocean and in Antarctica. That black carbon needs to come out of the stratosphere at some point, even though it leaks out slowly. And it seems it's probably going to leak out where we have snow now. Now that may, and so we need to understand what the effects of this are going to be. Are we going to get a nice albedo positive, the feedback coming from this black carbon? There's ways to estimate what the effect of this is. So I can tell you the sign of the effect, but you figured it out on your own. The question is, what's the magnitude of the effect, right? And how well do we know that? And then SON, it continues. So if all we were thinking about was global mean temperature, then upper stratospheric heating from absorbing aerosols can cool the planet, and it can do it more efficiently and more effectively than by reflecting. Once you start thinking about other changes, then it's not clear yet whether it is more efficient. Tropical cyclones do respond to stratospheric heating and cooling, and so in that regard, black carbon is more effective at reducing tropical cyclones than sulfate is at reducing them. But there's ozone decreases from the stratospheric heating with some compensation in the lower stratosphere. How robust this result, how big the compensation is, we need to understand it. We need to understand the exact mechanisms of it. And are there, when we start thinking about more sophisticated injection strategies rather than just uniformly 90 to 90, 0 to 360. And then the self-lofting increases the lifetime of absorbing aerosols in the upper stratosphere. And depending on your optimistic or pessimistic hat of your own knowledge of what might happen, that is either a good thing or a bad thing, right? And then stratospheric circulation concentrates the absorbing aerosols near the poles. So with that, I'll take any questions. Thanks.